Hello everyone. In this video, we are going to see one of the universal gate NAND. We are going to see NAND-to-NAND logic. Okay, and you are going to see why this NAND logic gate is called as universal gate. Okay, now in that matter, it is not only NAND and NOR both are called as universal gate. So we are going to show you the proof why it is called like that. So you are going to see NAND and NOR as universal gates. The reason is switching functions, that is AND and NOR, can easily be implemented using NAND and NOR gates. So you can switch the functions. So using NAND and NOR gates, you can always get the other fundamental gates like AND, OR or NOT. Okay. So since you can do that, NAND and NOR gates are referred to as universal gates. Okay. So you are going to see why it is. So you are going to use NAND-to-NAND logic. That means you are not going to use any other gates other than NAND. Okay, only using NAND, how to get AND, how to get OR, and how to get NOT. Okay, so you can see in circuit here. The first gate is a NAND gate, which has two input, that is X and Y. Okay, so when you have a NAND gate in between, you will get X dot Y the whole dash. So it is nothing but X NAND Y. Okay, so you can see the representation X dot Y the whole dash. You call it as X NAND Y. When you read it, you have to say X NAND Y. Now you pass it on to another NAND gate. What happens is you will have first input X NAND Y, and you got one more input X NAND Y. So since it has two input X NAND Y, two times has to be repeated. Now you will be getting X dot Y. So you, by seeing it, you want to understand. You need to prove it, right? So we are going to show you the proof. So remember what I said, X NAND Y. You have to read it as X NAND Y. So when you read it, you will see that first input, right? So that's the first input X NAND Y, and then second input again it is X NAND Y. Then you are going to pass it to a NAND gate. So you will get X dot Y. That's what you are going to prove it here. Okay. So you are going to see the proof. Now X NAND Y can be displayed like this, right? X dot Y the whole dash. This is the actual expression of a NAND. Okay, so you can call this as X NAND Y. Now by using De Morgan's second theorem, X dot Y the whole dash becomes X dash plus Y dash. Okay, so you are going to separate it by using De Morgan's second theorem. Now this is for one term, right? Now you are going to combine both the terms. So what happens here is the first term X NAND Y becomes X dash plus Y dash. Okay, based on this De Morgan's second theorem, you got this, and NAND, and again second term also can be written X dash plus Y. So once you prove it, you can write both the terms will be changed. Now you got a NAND gate in between. Again you are going to use the same logic, right? Now you consider this term as X and this term as Y. So what will happen is you will get X dot Y the whole dash. Okay, just write it as it is. Only thing you have to do is you consider this term as X and this term as Y. So what will happen? X dot Y the whole dash. So the whole term, that is X dot, the whole term that will be Y. Then you got a whole dash. Now again using De Morgan's second theorem, you will get, you are going to separate it, right? X dash plus Y dash. So right, you got X dash plus Y dash the whole dash plus X dash plus Y dash the whole dash. Okay. Now since you separated it, again the following terms, you can see two different terms. Again you have a whole dash. Again you can use the De Morgan's first theorem and then separate it. So what happens? This plus becomes dot. So X double dash dot Y double dash. Then plus this term X double dash dot Y double dash. Okay. So we understood what we are trying to say. Okay. Using De Morgan's theorem, you can separate it. Now you can see all the variables are separate. Now you know the involution law. X double dash equal to X. So that double dash will be removed. So it will be X dot Y plus X dot Y. Okay. And then you got another law, right? X plus X is X. That means X dot Y plus X dot Y, it will be identical term. So you can remove one term, and so you will get x dot y as the output. So you can see that x dot y. So using NAND logic, you can achieve AND operation. So finally that is a proof whatever you got. Now you are going to see OR operation using NAND gate. So since you have learned how to convert it, okay, it will be very easy for you to do this, because you are going to follow the same logic. You are going to use the De Morgan's theorem, and you can separate all the variables. Now here you can see two OR operations. First OR operation, you have two input, both are x, and second NAND gate, you got two input which both are y. So once you pass it on, you will get x dot x the whole dash, and here second one you got y dot y the whole dash. Okay. Now you can combine to another NAND, it becomes x plus y. So this is what you are going to prove. So when you pass on this x dot y the whole dash and y dot y the whole dash, it becomes x plus y. So you are going to see the proof. So it is x plus y equal to x NAND x NAND y NAND y. Okay. So since that is only difference between AND and OR operation. There you have x and y, x NAND y. Here you got x NAND x. Okay. Now you are going to take the first term. X NAND x can be written as x dot x the whole dash. Okay. So you can convert it using De Morgan's second theorem. So it becomes x dash plus x dash. So again you got two identical terms. Okay. X dash plus x dash will become x. Okay. So you made this term as a single term x dash. Now the same way y NAND y also can be converted, and you can get it as y dash separate. Same logic you can use, you can get y dash. Okay. So you got x dash for this and y dash for this. Now you got a NAND gate in a NAND operation in between. Now you can write x dash NAND y dash. Okay. This is the left hand side is the expression, the whole expression. Now right hand side, since you converted this, okay, first term becomes x dash and second term becomes y dash. You are going to write it x dash NAND y dash. Now you are going to use the NAND gate, so it becomes x dot y the whole dash. Okay. Now using De Morgan's second theorem, this dot becomes plus. Okay. So you got the x double dash plus y double dash. Okay. Now since you got double dash, you can use involution law and you can change it to x plus y. So you can see the final expression, that is the OR operation. Okay. So using NAND logic, you can achieve the OR operation. Okay. Then finally you got NOT operation. You got an input as x. Okay. Two input x and x NAND. It becomes x dash. Okay. So you can see not x equal to x NAND x. Okay. So x NAND x is nothing but x dot x the whole dash. Okay. Now x dot x the whole dash will become x dash plus x dash. By using De Morgan's theorem, it will become x dash plus x dash. Again you got identical terms, that is x dash. So you are getting x dash, that is x dash plus x dash is x dash. So that is nothing but the NOT operator. Okay. So you are going to see how to use the rule to convert a normal expression into a NAND-to-NAND logic network. Okay. So for example, they will give an expression like this. Okay. They'll ask you to convert it to a NAND-to-NAND only gates. That means you are not going to use any other gate, you are going to use only NAND gate. So you are going to see that derive simplified sum of product expression. So you are going to get sum of product expression. Okay. Now you are going to draw the circuit diagram using AND and OR gate. That is the normal thing you will do. You will be drawing a circuit using NOT, AND and OR gates. Then just replace AND and OR and NAND and NOT gate using NAND gates. That's what you are going to do. So for example, x dot y dot z dash plus z dot x dash can be drawn as follows, assuming that that inputs and their complements are available. So you already seen in the previous video how to draw a logical circuit using the gates. So you know that a NOT gate will come first, then AND gate, then OR gate. So you are going to draw the first term x, y, z. So you got z dash here in the first term. So z NOT gate becomes z dash. Okay, then you got 3 input which is combined to an AND gate, okay, as input, and so you'll get x dot y dot z dash. So that's the first term. Second term we got 2 input z and x dash. So x dash you have to pass it on to a NOT gate, so it becomes x dash, and then you got z. So when you pass it on to an AND, it becomes z dot x dash. So you got 2 terms. Now you are going to use this OR operation and then combine it. So when you use an OR operation, you will get the final term. So this is how you have done previously. Now after drawing this, okay, this is what you call AND to OR implementation. Once you have done this, you are going to convert each and every gate into a NAND gate. So you can see here, just you can notice, two NOT gates has been converted into 2 NAND gate. AND gate also is converted to NAND gate. OR gate also is converted to NAND gate. The proof has been already achieved there, that you all know. You can always convert NAND to NAND to any of the operation, whether it is AND or NOT. You can convert it. So that's the reason they just simplify. That is, they are not showing any proof. Just draw the normal circuit, convert everything into NAND. Nothing else. So when they ask you an exam, just write the expression, draw the normal circuit using AND or NOT gates, and then convert every gate into a NAND gate. So once you do that, you know that it has been implemented. So if they ask you NAND to NAND only logic circuit, you can show it like this. So you can try out the expression which is given here. So you can see that 3 expressions are given. You can use draw the diagram of a digital circuit for the function using NAND gates only. This is how you will get in exams, NAND gates only or NAND to NAND gates. Okay. Now you can draw the circuit diagram normally using AND and OR, and then convert it into a NAND gate. So all the gates has to be drawn using NAND gates only. So once you draw it, your circuit is ready. So try out these 3 questions in your notebook. So hope you understood this video. We'll meet you in the next video. Till then, thank you.